Suppose you have 4 pigeonholes, and suppose you have a number of pigeons that are distributed throughout these pigeonholes. If you have exactly the same number of pigeons than you have pigeonholes, in this case 4, then there is a way in which you can have no pigeonhole with more than one pigeon. Namely, for every pigeonhole you have one pigeon. But the moment you get an extra pigeon, this isn't possible anymore. At least one pigeonhole will now have to shelter more than one pigeon. That's what the pigeonhole principle says. If you put more objects than containers, then at least one container must hold more than one object. In our case, we have 4 containers and we have 5 pigeons, which means that at least one container will necessarily have more than one pigeon. It is a very simple principle and yet a surprisingly useful one. Let's use it in a more interesting example. Suppose you're at a party with 13 people. Show that at least 2 people were born in the same month. Let's start by stating that there are 12 months in the year. These are like the pigeonholes. And we also know that there are 13 people. These are the pigeons. By the pigeonhole principle, since 13 is greater than 12, at least 1 month must have 2 birthdays. And the proof is done. Let's see another example. Take any list of 6 integers, a1 to a6. By the pigeonhole principle, we know that there exists indices I different than j, such that ai equals aj mod 5. Or, said in another way, we know that 2 of these integers must give the same remainder when divided by 5. Why is that? Well, the possible remainders when dividing by 5 are 0, 1, 2, 3, and 4. So if this is a set of remainders, we know that the size of the set is 5. There are 5 elements, 5 possible remainders. These are our pigeonholes. And since we have 6 numbers, at least 2 of them must fall into the same pigeonhole, meaning they have the same remainder. So that's the pigeonhole principle. More pigeons than holes guarantees a shared hole.